right. So, I'm sure you recall the danger to the fish in the pond. We've looked at potentially acid poisoning. We've looked at bases poisoning the fish. We understand that the glass factory is an issue here. What we're looking for is we want a way to keep the pH of the pond stable. We want the pH to remain in a fairly narrow range. For living organisms to function, there's a whole series of proteins that you have that do a bunch of catalytic work and a bunch of different cellular processes. Protein structure, the shape the protein takes on, is highly dependent on the pH in addition to temperature. So changes to pH change the effectiveness and can completely break, denature those proteins that drive a lot of the biological activity that keep you and the little fishies alive. So what we need to do is we need some way to minimize changes to pH, to keep the pH more stable than it is now. And to do that, we use something called buffers. Okay? A buffer is a substance that minimizes pH changes in a solution. So we're going to add this buffer stuff, and then if acid or base is added later on, it will minimize, keep the change in the overall pH as small as possible. Okay? Buffers fundamentally are formed when you add a weak acid or base and its conjugate. So I'm going to have two bottles. I'm going to have a bottle of weak acid and a bottle of its conjugate, some sort of conjugate salt of the weak acid. And I'm going to add both of them. And the idea here is that if we imagine our sort of typical weak acid, our ethanoic acid, and its conjugate, okay, I want to add both of those. If I have both of these things in the solution, then that equilibrium, the fact that I have both of these, allows the solution to react with bases. If some hydroxide ions are created in the solution, somebody dumps in some sodium hydroxide, that hydroxide ions would react with the acid that I already have there, minimizing the change to the pH. Probably not stopping it entirely, but certainly minimizing it. And because I have both of these things in the solution, by having some of the conjugate base, if somebody dumps some, say, hydrochloric acid, which would be a source of hydrogen ions, the conjugate would react with the hydrogen ions to produce a little bit more of the acid. But again, minimizing the pH change. By having both the weak acid and its conjugate, it can react either direction, either with acid or with base. Fundamentally, the equilibrium that we're looking at is this equilibrium. Notice that these two reactions are written as going just to completion. And that's exactly how we're going to deal with these types of problems. We're going to calculate the buffer by itself. We can calculate the equilibrium. We're going to have this Ka value. But the reactions that take place, anything we add to it, any strong acid or strong base we add, we're going to assume that that strong acid, strong base reacts completely. And then we'll go back and look at the equilibrium and recalculate based on the changes that the strong acid or strong base have created. So, step one, let's look at how do we deal with this equilibrium for a buffer. It's going to look like a very typical equilibrium problem. Right? I'm going to have this equilibrium taking place, though acetic acid and acetate ion. The difference, the only difference, is that instead of starting with just some acid and having a 0 and a 0 here, I'm going to start with some acid and some of the conjugate ion, because I've added both of them to the solution. I do the same set of steps. I have x's. I'm going to solve for that x value that's going to represent the amount of hydrogen that's formed. So I'm going to have some number, 0, some number in an ice diagram. And that's the way I'm going to go through and do the equilibrium part of this, which we need to practice before we go into, okay, once I've got that equilibrium established, what happens if somebody comes in and tries to mess it up, which we'll do in a minute. All right? So let's take a look. Same idea, same stuff we've doing. In fact, you've already really looked at problems like this. I have some reactants and some products both at the same time in the equilibrium. That's all this is. This is a problem with some reactants and some products. So, give it a shot. I'm going to make a buffer solution that contains 0.5 molar acetic acid. And I'm going to make a buffer solution and that same solution is also going to contain 0.5 molar sodium acetate. Here's an important question. Does the sodium ion participate in this reaction? Was it part of the equilibrium we saw before? Do sodium ions generally ever participate in any reaction we've ever seen? No, sodium ions, they've already given up their electron, inner core electrons, very tightly held, very unreactive. The sodium ions are going to be our spectator ions. So, almost always. 99.999% of the time, sodium ions aren't going to do anything. Okay? You could do some crazy stuff and get them to do things if you add electricity or do some crazy fun stuff like that, which we haven't got to yet.
For the AP test, will we have to know all of the acetic acids that, or will they tell us what
So acetate was on the things to memorize list. The acetate ion. Ethanoic acid, acetic acid, you should have that memorized. It's the one we use a lot. Go. So, with respect to memorizing the periodic table, you need to know those names and symbols. Because if you look at our periodic table that they're going to have throughout the test, you always have a periodic table, just like the one we get on our test. It has no names.
But I mean, what are the odds they're going to use something like
Protactinium or whatever? Very low. Very, very low. Yep. I want the pH, so that's going to be the concentration of hydrogen ions. So I put these two things together. I'm not at equilibrium. The system shifts to equilibrium. That's going to produce more hydrogen ions. Forming a buffer is when we have the acid, the weak acid, and the conjugate both in the solution. Okay? All right, let's keep going on this. A lot of confusion, okay? So let me make this perfectly clear. You have done these problems many times already. Okay? Last unit, you did a bunch of problems exactly like this. You need to understand, you need to generalize your knowledge, okay, from last unit to this new situation. We have a basic equilibrium. This is the equilibrium. This is the equation described by Ka. And you need to realize that. Remember, acid dissociation constant. Ka, the acid part means an acid giving off its hydrogen ion to produce its conjugate. It's really important, okay, because it's going to save you a ton of time and work if you can get that down. So, acid dissociation, Ka means an acid breaking apart. That's what this Ka means. I don't care anything about what other stuff they told you or anything else. If you see a Ka, it's for this acid breaking apart.
So basically like the NaC2H3O2 is there kind of to...
We'll get there. We'll get to it. The key that you need to realize is you need to link in your head Ka means an acid breaking apart. Don't try and create some new crazy equation. Ka, that's what it means. Kb means a base reacting with water.
Wait, so
always.
A Ka equation will always have H plus.
We'll always have some acid to make H plus and some negative ion. That's what it's going to be. The base, Kb, is a base reacting with water to produce hydroxides and some, conjugate acid. So, how much of this stuff do I have in the solution at the start? What's my initial value? 0.5 molar. So, 0.5 molar. Did I add anything, any hydrogen ions? No, I didn't add any strong acids. Strong acids would be a source of hydrogen ions. They're completely disassociated. Weak acids are not. We assume we're going to, in our heads, we're saying, we're trying to figure out how much it breaks apart. So it doesn't break apart any at the start. Now, here's the big question. Did I add any acetate ions? Look at this. NaC2H3O2. That's the acetate ion. The Na, what does it do? It splits apart. This is totally soluble. So really, this is a source of acetate ions. Sodium ions are spectators. They are not going to react. Compounds with sodium ions in them are totally soluble. They are going to completely split apart.
So could we think of Na
You can
the same
think,
way as we could think of like nitrates?
yeah, exactly. Nitrates, in fact, that's what the rules say. Yep. So this is really, the sodium acetate is really our source of acetate ions. So, what value am I going to put here? 0.5. I'm going to put 0.5. Okay? Guys, that's my starting value for the acetate ions based on adding this stuff. This stuff provided 0.5 molar acetate ions. Yeah, there's some sodium ions, 0.5 molar sodium ions, but they don't do anything. They're not part of this equilibrium. They're not going to do anything in the solution. They're unimportant for this, any type of chemical reactions that we're working with. Not to say they're not important overall, but in the chemistry we do, alkali metal ions don't do anything. Ever. Those are less soluble, so those might precipitate with certain compounds. Well, there was a set of things I asked you to memorize around those kinds of things. Slightly soluble and stuff like that. All right, so now, once we've got that, once we've identified that, hopefully we're starting to get back on solid ground. The new craziness was, hey, how in the heck do I deal with this sodium acetate? Because now we're back to a totally standard ice diagram problem. Which way does this have to shift? I have to shift to the right. I have 0 of this stuff. I have to make it. So I'm going to use up this. I'm going to make 0.5 x 0.5 plus x. So, now, if I said, what is the equilibrium expression? You're going to write Ka equals concentration of the products over the concentration of reactants. This is a chemical equation. This is the equilibrium expression. You need to know what to write if they say write down the equilibrium expression. Right? So this is the equilibrium expression for this Ka value, this equation. We can substitute these values in. And now we can use our 5% rule. 0.5 plus x is about 0.5 minus x is about. So let's make that simplification. So, important question. How did I know that? How did I think I could do that? This Ka value is really small. And look, I already have a bunch of this stuff. This x value is going to be tiny. It's actually going to be a really small number. So small that if I take 0.5 plus x, it's going to be 0.5 because my equilibrium lies far to the left. Remember that K value represents the ratio of products to reactants. So you can generalize it and just say, hey, this is much less than 1. I already have a bunch of each of these things. That Kx value is going to be small. So this cancels out, and yeah, x is 1.8 times 10 to the negative 5. In this case, it worked out so that x was equal to Ka. That's okay. It won't always happen that way, as we'll see in a bit. So now, that's our concentration of hydrogen ions. Take the negative log of it to get the pH. 4.74. So, take the log of the value, take this number and take the log of it. and then change its sign. Log is a button on your calculator that says log. If you take your iPhone and turn it sideways, there's a log button on there. Get the scientific calculator. All right, shh, we're not done. There's another layer of complexity we have to add to this. So gentlemen, shh, quiet. Okay. Kyle, I can't hear. Shh, gentlemen. So, this is important. It's important enough that everybody needs to know this, right? When we say Ka, we are describing the equilibrium of a chemical reaction. And the generic form, the sort of made up form, is an acid HA, where A is some negative ion. Okay. Reacting with, or breaking apart, dissociating, to produce the hydrogen ions and A minus. And so this acid could be lots of different acids, any acid. Okay? So it's the producing hydrogen ions. Anytime you write an acid dissociating in this way, the equilibrium that's represented we call Ka. And if you're dealing with Kb, we're talking about some base B dissolving in water, creating Hb plus and hydroxide ions. Okay? And what can this B be? It could be ammonia, it could be a methylamine, ethylamine, lots of different stuff like that. It could potentially be an alkali metal, sort of. Yes, they produce hydroxides. It's an alkali metal oxide would be better. It's a little bit more complex when you start to talk about alkali metals, but they do sort of function the same way. Those reactions, however, are not equilibrium reactions. Shh. Question.
So do the reactions, do like certain reactions have both the Ka value and the Ka value?
No, but you can, so this is our Ka, we can write a Kb based on this. Do I want to see what's going on outside? Okay, we got to get through this, so let's pretend that it's all okay outside. Okay, so see, this would be Kb, but it would be the Kb of the conjugate of this acid. Is that same A minus? Questions? Then we got to move on.
So water doesn't matter for acids, right?
Right, you can leave you could put water in here and this would become H, but we don't, it doesn't do anything.
Okay, and also when it is an
Amphoteric substances
Yeah.
can do both of these.
yeah, but how would you?
It depends on the situation. Depends on what it's reacting with.
So we would have to choose either.
The problems will generally make it fairly clear. Like if you have this amphoteric substance and you add an acid to it, it's going to function as a base. Have this amphoteric substance, you add a base, it's going to function as an acid. So it depends on what it's reacting with. Neither of these equations, none of these are that. This is a base reacting with water to produce an acid. Yeah. It's an ion that functions as a base. Because this is a Kb. And so we wanted to see, hey, look, this is Ka, but we can take the conjugate and get a Kb for it. All right, so, gentlemen, I'm going to make your lives easier. We've been doing this ice diagram stuff a lot. We've been making this 5% rule assumption a lot. Okay? So instead of always doing it, do the whole problem out, do the whole problem out, there's a way in math that we can make things easier. What if we did this symbolically? In other words, take the symbols and rearrange them in the same steps that we've been doing to generate an equation that will sort of do it all in one step. All right? That's called the Henderson-Hasselbach equation. So, here's our equilibrium expression, right? This is basically what we solve each time. What do we almost always solve for in this problem? We're almost always looking for H plus, so let's rearrange this to solve for H plus. Now, what do we usually do with that H plus once we found it? We usually take the negative log of it, so let's take the negative log of each side. And that would give us what we know as the Henderson-Hasselbach equation. So, whoa, slow. Listen. What does P mean? Take the negative log. So negative log of the hydrogen ion concentration. Negative log of the Ka value. And then because we have this ratio, we flip it around so we get plus the log of A minus. What's A minus? That's the conjugate from the equation, right? That's the conjugate acid.
Okay.
What's HA? That's the acid concentration. So, where do we think you might find this equation on a test? Hey, it's probably on the useful equation sheet. So, it doesn't matter. So that you don't have otherwise you have a negative sign here. Same difference. So, listen. You can, guys, we got plenty of time, so relax. So, you can have a negative sign here and flip these back around. Okay, but that's not how they write it on the useful equation sheet. So I wanted to go with what's on the useful equation sheet. But it's the same math. So there are two versions of this on the useful equation sheet. One exactly like this, and one that says POH. And the POH is going to be based on this equation and solving for the hydroxide concentration. Okay? And it will have Kb instead of Ka. All right? But both of them are on here. Make sure you understand where they are, because they're useful. Questions?
So, the A in the problem we just solved the pH for would be the C2H3O2.
Yeah, -1 charge.
A would be the
HC2H3O2. Yep, that's the acid, and then its conjugate base. Now, notice, most of the time, what are we plugging into that equilibrium expression most of the time? We're plugging in like some number minus x. We're actually using initial concentration values. And these values are all supposed to be equilibrium values. But we're making our 5% rule assumption that says, hey, the initial value is basically the same as the equilibrium value. So this only works if the initial value is the same as the equilibrium value. 203. So the initial, this only works if the 5% rule works in the way that we've been using it. Okay? We're plugging in initial values here. And that works fine if the 5% rule works. So again, small Ka values. We'll apply it in a sec, okay? So here's the situation. Here's a very typical type of problem. We are going to set up a buffer solution. In fact, we just did. We're going to take that same buffer solution we just set up, and we're going to add some strong base to it. We're going to take that solution and we're going to disturb it. We're going to mess around with it. We want to calculate what happens. The way that we're going to do that, the way we're going to think about is breaking this problem into two steps. Step number one, if you add a strong acid or a strong base, we're going to assume that those things run to completion. So we're going to do a stoichiometry problem first. I'm going to show you a quick way to do these stoichiometry problems. And then we're going to take the results of the stoichiometry problem and say, hey, that's the new initial conditions, and recalculate the equilibrium. Okay, redo that equilibrium problem we just saw. So, here's the idea. We have 1 liter of the solution we just made. I'm going to add 0.01 moles of sodium hydroxide to it. If I took 0.01 moles of sodium hydroxide and dissolved it in water, the pH would be 12. Right? I'd have 1.0 times 10 to the negative 2 molar hydroxide ions. Sodium's not going to do anything, right? Strong base, please splits apart. Sodium's not going to do anything. So I'd have a lot of hydroxide ions in there. What I want to know is what happens when I add that same amount of sodium hydroxide to a buffered solution. Step number 1, I have a chemical reaction, stoichiometry. This base, what's it going to react with in my buffer? With the acid. Base is going to react with the acid. My acid is ethanoic acid. So the hydroxide ions react with my acid. Okay, and they're going to produce some water, which I don't really care about, and some more acetate ions. Now notice, this is a stoichiometry problem. But what I want to know from this stoichiometry problem is how much acid do I have left and how much acetate ions do I have at the end? So if I'm adding a base, so it reacts with the acidic part of the buffer. If I added an acid, I would reverse this equation to a certain extent, and it would react with this. So a buffer has both an acid and a base. We use a weak acid and its conjugate, so it can go either way. So I know that I have 0.01 moles of this stuff. Now I used a volume of 1 liter so that I know how many moles of this do I have in the solution. 0.5, because we had, remember, if you look back at the previous problem, it was 0.5 molar. So I have 0.5 of this. I don't care about the water, and here's where we're going to deviate from our normal stoichiometry. Normally we just go, okay, let's do those two and go. But what I really want to know is how much of this stuff do I have, because I started with some. So I'm going to shortcut this process a little bit and say, how much of this stuff did I start with? Same 0.5, 1 liter times 0.5 molar solution. So I have each of these guys to start with, but again, I'm not doing this as an equilibrium problem. I'm doing this as a stoichiometry. I'm going to say I use up all of the strong base. It gets completely used up. That's the assumption we're doing. That's our simplification to make this problem. Instead of trying to solve multiple equations at the same time, we're separating them temporally. What really happens in real life is this reacts some in the equilibrium that comes slowly to equilibrium. We're saying it goes to completion and then comes back to equilibrium. So if I use up 0.01 of the hydroxide, how much of this stuff did I use up? I used up 0.01. How much of this did I make? 0.01. So I know that I have none of this left. That was the whole point. And I have 0.49 of this. And I have 0.51. This was a stoichiometry calculation. I ran it to completion using up all the base. Now, I'm going to take these two values.
And the base is the buffer.
The base is not the buffer. The base is the sodium hydroxide I added. The buffer is the solution that contains this stuff and this stuff. The buffer is the weak acid and its conjugate. The base is the sodium hydroxide I added that reacted with it. Now I'm going to take these two values and use them to solve a new equilibrium problem. I'm going to recalculate where is the buffer now based on these starting values. So I'm going to go to this equation and I'm going to say, hey, my starting value for the acid is 0.49. Again, I'm sort of imagining rewinding the clock, so I'm starting over with new calculations, 0 hydrogen ions, and my base is going to be 0.51. That's the difference of adding that base, adding that sodium hydroxide. It shifted a little bit of the acid to be the conjugate. And so I'm going to redo these calculations. Minus x plus x, the same process, right? Nothing new to see here. Same equilibrium, except now, is there a quick way I can solve this? I've got the Henderson-Hasselbach equation now. So I can just plug into this equation. Yeah, they're a funny guy. So I'm just plugging these values in. I know my Ka. I can solve the pH. So remember, if we had added that sodium hydroxide to pure water, the pH would have been 12. We added it to this buffer, the pH is 4.76. It went from 4.74 to 4.76. The buffer minimizes the pH change.
Can you explain again why we assume that all the OH is used up?
It simplifies our work. It gives us very close to the same answer, and it simplifies our work. It's also not a bad way to think about this. Adding this strong base, we can assume that it gets completely reacted and then recalculate the equilibrium. The other way to do this would be to say, well, the base gets used up and comes to some equilibrium. But then we have to do this equilibrium at the same time we're working with that other equation. You'd have multiple equations and multiple unknowns, and it would be really messy. This is a really good approximation of that process. What we say is it goes to completion, and then we're calculating coming back, instead of starting here and coming to the middle, which is a much trickier calculation. Okay? The worksheet that we handed out, 2009, the last part of that is really this. It's not listed, it doesn't talk about buffers, it doesn't talk about it, but it's the same kind of process. You do a stoichiometry calculation, and then you use the results of that in an equilibrium. It's not exactly the same problem because it's not really dealing with buffers. But you're doing some stoichiometry with one equation, you're taking the results of that and putting it into your equilibrium. The 2005 I handed out today is directly this. It is this exact kind of problem, where they create a buffer, they add some stuff to it, do a stoichiometry, then do your equilibrium. And we're going to drive this point home tomorrow when we start to talk about titrations. Okay, because it's the same process. Stoichiometry with the strong acid or strong base reacting with something weak, take the results of that, plug it into the equilibrium. All right, we got to get this pond under control. We have this idea about buffers. We can control the pH of the pond and keep it stable, but let's look at going back to the source and trying to really neutralize what's coming out of the glass factory. That would help us out.